Yesterday, I introduced you to half adders and full adders. And now we're going to see how we can put them together, right? So how we use composition or integration to actually make a working circuit that can actually add two numbers, right? It will be adding two binary numbers, but of course, as you know, any number, no matter how large, in any numbering system can be converted to binary. We'll start from this slide. So do please, you know what, hold on, sorry. There was one more thing I wanted to point out. And before we start the lecture, also important, having to do with Okay, so I fleshed out the outline, the course outline for the last, I guess, a week and a half or 2 weeks of the session, right? So right now we're going to go over adders and subtractors, and then we're going to go over controlled input, and then we're going to go over flip-flops, right? Flip-flops is the elementary method of storage, right? So far, we've been only processing signals, sort of processing bit values with some inputs and some outcomes, right? But we haven't actually stored any bits, right? We haven't stored even one bit. And of course, you know, the most important part of actually having a computer that can do things, right, is for it to be able to store values in its operating memory, right? I'm not even talking about permanent persistent storage like hard drives and flash memory. I'm talking about operating memory, right? So in order for these signals, ones and zeros, to go into our circuits, they have to come out from somewhere, right? That information has already to be there. In order for it to be there, it has to be stored. And there are a number of ways to do it. And I think the simplest one is called the flip-flop or flip-flop gate. Okay, and then the last thing that I will cover is going to be a racetrack problem, right? The racetrack problem is a particular example of general concept called race conditions, right? So after that, I think we will have time for review. And then very importantly, we have, so we're going to have a class right now, a class tomorrow. Then we have a long weekend, the 4th of July, and I'm actually going to assign a bit of reading. And also you will have time to catch up on some of the homework over the weekend. After that, we have 3 lectures in this last week. So we'll have flip-flops, racetrack, and review. And the exam is going to be on the Monday after the final weekend, and then we're going to be done. I received a few emails regarding regrade requests. I will answer them. I'll check. I try to make sure that there should be no issues, but it's possible, right? So I'm going to check, and I'm going to, if necessary, adjust your score. Oh, another important announcement. Most students did well on this midterm, but some students did less well than they expected. Some of very good students in this class, right? Now that you're familiar with the format, I expect everybody to do better on the final, right? I expect you to prepare better. And just another issue that some people brought up was time pressure. Right? So I'm going to try to alleviate that by allocating more time for the final exam, right? Even though it's going to be at the regular class time, but we'll have to figure out how to give everybody enough time, because I want to make sure that you understand the material and can do the problems, but I don't need you to do it under the threat of a stopwatch, right? So it's not my goal to have you like do it as fast as possible. My goal is to check that you actually learned how to do these things. So I don't want the time pressure. Because I expect everybody to do better on the final exam, I'm going to encourage improvement. So what I will do is that when I'm tabulating the grades, if you do better on the final exam, let's say that you got 70 on the midterm and 80 on the final, right? I'm going to count the final score as if you also got it on the midterm. If for some reason you did really well on the midterm and then you did a little bit less on the final, that's fine. You know, they will be calculated as they are. But if you made an improvement on the final, then the final grade will count for the final, and it will also replace the midterm grade. Any questions about that?
Will the final test everything that we've learned so far, or just like the second half? I forget.
Yeah, it will be mostly about the second half, but I may throw in a couple of questions about the first half. But it will certainly, most of the questions are going to be about second half. And keep in mind that second half started before the midterm, right? The last thing that was on midterm, I think, were compound operators, right? I'm not sure that we even had logic. I don't recall. I may have put logic gates on the midterm, but canonical forms level say that again.
You put logic gates on the midterm.
Okay, but that okay, thank you. But that was the last thing that was on the midterm.
Yeah.
So the second half, everybody pay attention. The second half of the semester started on 6/15. So canonical standard forms, regular standard forms, midterms, you know, all of the minimization, all of that is going to be, a lot of it is going to be on the final, right? And then of course the K-maps, the 7-segment display, the tabulation method, the prime implicant table, right? The others and subtractors. So there's a lot of material to cover on the final, and most of it is going to come after starting with 6/15. But I may throw in some of the earlier material that is relevant. Okay, I'm not going to give you, you know, radix equations, right? I'm not going to do that. But there, I may ask you some questions from the first half that has immediate bearing on some of the topics in the second half. Any other questions on that? Okay, but yes, I want. It's just that I think because of the time pressure, several students spoke to me who I know are very good students, and they didn't do well. I think that they are certainly going to do well. Everyone, I hope that everyone does better on the final, and that will, you know, improve your grade. Okay, I think. Oh yes, regarding reading, right? As I said earlier, the book is not, or the lectures, right, don't really follow the book. You know, in some cases, I was able to find relevant readings in the books, but in other cases, the book sort of goes into slightly other territory that is related, and I don't need you to read the whole book, but I do want you to read certain chapters and learn from it, and that I will ask about that on the exam. So so far we've been mostly in chapter 3, right? So we had, well, let's just look at the readings real quick. We have some readings from chapter 1. I hope you did them. If not, quickly review. Then we did a lot of chapter 2, right? Where we had the axiom, the theorems, the properties, the logic gate operations, logic gates, all of the canonical standard forms, all of that was in chapter 2. The K-maps are in chapter 3. Notice, though, that the don't care conditions, that the tabular method and the prime implicant table are not in the book at all. So I have some external readings. You should do them. I didn't assign it initially, but over the weekend, I would like you to read, even though I put it here so that because that's where the room was, but I haven't assigned it before the 4.3. right, from the from the fourth chapter. I would like you to read 4.3, and then now I'm assigning 4.4 and 4.5. Okay. Then later, when we get to controlled input, you will have to read 4.11. All of these are very short. It will not take you a lot of time, but I want you to do it. And then for flip-flops, we'll have just one thing out of chapter 5. There is nothing on the racetrack problem in the book, so I have a little bit of external reading. So do as much of the reading over the weekend as possible. And I think this is all that I need to say about the outline. Okay, so now we go to the lecture. Okay, so we learned about half adders that are obviously simpler because they only have 2 inputs. And then we also learned about full adders, right? And one of the homework assignments was to, assuming that you have a simple half adder, let's say you integrate it and make it into a single thing. So how can we make a full adder out of 2 half adders, right? So many of you, came up with a way to do it, but it was a challenging task. So I didn't need you to submit it yet. So now let's go over it together, and please pay attention. So first of all, let's see what we expect these things to do, right? So a full adder should be able to take 2 inputs, 2 bits, right, in the same column. When you're adding 2 binary numbers, you're going to have a full adder for each digit in order for the whole thing to work. So a full adder needs to be able to add the 2 bits, one from the top number, one from the bottom number. We'll call them A and B. But it also needs to be able to accept and add the carry in that came from the less significant digit right after it. Okay, and again, if anything isn't clear, just stop me immediately. Okay, because here we're putting everything that we've learned so far together, and we're going to make it, not physically, but schematically, we're going to make a circuit that actually is useful. Okay, so we're going to add them all, right? And the result is going to be the sum, but that sum will only have one binary place. It's going to be just one binary digit. And of course, if A, B, and C are 1, then the sum is going to be 3, right? And of course, we cannot represent 3 by a single digit. So for that reason, we're going to, in addition to the sum, that could be either 0 or 1, we're going to have a carry out, right? So full adder takes A, B, carry in, produces sum, and carry out. Keep in mind that this carry out, it will go to the left, which means that its significance, right, it's 1 order of significance higher than, let's say, the sum, okay? Because let's say that this were a decimal adder, right? It would work in a similar way where you would get some kind of some decimal digit, I don't know, 5, and then let's say that the carry out was 1, right? Well, that 1 would represent not like ones, but it would represent, right? So just keep in mind that in this representation, sum is 1 decimal place less significant than the carry out. Okay, again, question, ask me now. So that is what we expect this full adder, when it's done, to do. Now we're going to use 2 half adders, right? So this is half adder 1. So half adder 1 will also take, so half adder 1 would be sufficient to add a single digit binary number, or we can use it to add the least significant digit of a larger binary number. So it takes, again, 1 digit from A, 1 digit from B, adds them up, and produces a sum. We're going to call it sum1 or S1. And its carry out bit we're going to call C1, right? Because it's half adder 1. Now, why do we need this carry-out bit? Well, the sum would be sufficient if both are 0, a is 1, b is 0, a is 0, b is 1. But what if both a and b are 1, right? We cannot get 3, but we could possibly get 2, right? And if we get 2, then what would be the values of S1 and C1, right? If both a and b are 1, somebody quickly, what will be the values?
S1 would be 0 and C1 would be 1.
Exactly, right? So we would get binary 10 or 2. Okay, so let's move forward. Now let's look at the second half adder, right? So internally, both half adders are exactly the same. They work exactly the same, right? So the second half adder will also take only 2 inputs, A and B, but because we're going to use them sequentially, or put them together sequentially, instead of A, we're going to send the sum of the first half adder as an A input to the second half adder. And then we're going to take that, we're going to take A carry and send it in as B, right? So now we're adding S1 and carry in, right, in the second half adder. And again, it works similarly. It will produce a sum and its own carry out. We'll call them S2 and C2, carry out 2. Okay. Now, figure out how to put them together. So we know that those half adders work because there are a bunch of gates inside them that let them do this, right? Take 2 inputs and produce 2 outputs. But now we're going to, let's say, make them, put a very small drop of epoxy on top of them, and now it's an integrated circuit, and we don't need to care anymore about what's inside it, right? So we're going in our diagram represent them just by the square, black or red box. So we have half adder 1 and half adder 2, and now we need to connect the wires just right so that together they end up doing this. So we have our 2 inputs, 2 initial inputs, A and B. Question.
I'm sorry. What is the difference between the HA1 in a circle and HA1 in a rectangle?
Well, no difference actually. They're exactly, well, not only, so the 2 half adders are the same, whereas whenever we say half adder 1 in different places in this slide, we're literally talking about the same thing. So, here we here we figured out, what it needs to do. Okay, now that we know it, we're going to, represent it as a red box, right? And it's a red box that will take 2 inputs and produce 2 outputs. That's it. So we have 2 initial digits, A and B. This half adder will produce a sum, S1, and we're going to send it into the second half adder as its own input, right? So both half adders will work the same. Now, also the first half adder will produce a carry out, and we'll set it aside for now, where we're not directly sending into half adder 2. Now, question. This whole thing eventually, right, when we're done with it, will represent a full adder. So what is missing right now on the left side of this diagram?
The C-in.
That's right. Was that Chelsea?
It was Anna.
Anna, okay, that's right. Anna is exactly right. The full adder has 3 inputs, right? The A and B and the carry in that it got from the less significant digit or addition on its right? So we need to draw that in a second. And there it is, right? So the full adder has 3 inputs, and this is the 3 inputs, and you want to always have them on the left, like in a column, right? Don't start, creating inputs in the middle. So we'll have a long wire that will take that into the second half adder. So what we have here, the first half adder will add the 2 digits from the numbers, and the second half adder will take the resulting sum and add the carry to it. So the work is almost done, but not quite, because the first half header produced a carry. And even if we sort of like set it aside for a moment, could the second half header produce its own carry that is non-zero?
Yes.
Absolutely, right? So the second half header will produce its, let's call it the resulting sum, which is going to be the resulting sum, the bit that will go under the addition. We'll call it S2. So this will be part of the result that will come out there. But it could also produce its own carry, and this carry could be 1, could not be more than that, right? So if both A and B are 1, then the sum is going to be 0, and the carry out is going to be 1. So that could happen. So now we know that this is going to be part of the result, but we have so far these disconnected dangling carries. Okay, so let's see how we can sort of tie it all together, right? Any ideas? What do you think we should do with C1 and C2? Should we just add them, or is it trickier than that? Right. So this whole full adder, once it's done, and we can integrate it into a single device, needs to produce a sum and its own carry out. So we already got the sum. Now we need to take these two carries and somehow make a single resulting carry out. So
we should OR them, because let's say our first two inputs, like our A is 1 and our B is 0. We get a sum of 1 and we have a C out of 0. And now in our second half adder, we have our S1 was 1, right? And if we have a Cn of 1, then our second C out will be 1, right? Yeah, so we have a 0 and a 1. And if we add that, there'll be 0, but we do have a carry out, so we need to OR them.
Okay, that is good. Yeah. So we're going to just test that in a second, right?
Do we need to have another half adder?
Go ahead.
Sorry about that.
We cannot add another half adder. We have to work just with these, right? We need to, yes. So just 1 second. Let me just answer that question, and then then I want to hear what you're saying. So we only have half adders by the spec of the problem, the assignment, and you can use another gate, right? You're not going to be adding them, right? But you can AND them or OR them or NOR them or I don't know, XOR them or NAND them, right? But you cannot have a second half adder, a third half adder. Okay, continue, please.
Well, now that I think about it more, I think I might be wrong, but I was thinking exclusive OR, because then if they're both 1, it'll be 0, but then I don't know where the 1 would go, so never mind.
All right, no, but all ideas are good. So let's sort of like test different inputs, and the proposal was the first proposal was OR, right? So if let's say that both are 0, right? Then the sum is 0, carry out is 0. Then we have 0. There was, let's say, no carry in, 0, sum of 0, C out is 0. We can OR them and it's 0, right? What if in the example that was proposed, what is if one of them is 1, right? Then the sum is going to be 1, the carry is going to be 0, right? Then the sum is going to be 1, the S2, carry is going to be 0, that's fine. What is both of them are 1, right? If they're both 1, S1 is 0, carry out is 1. Okay, then we have here 0, let's say there was no carry in 0, the sum is 0, this carry out is 0, but if we OR them, right, we still get carry 1, which we want, right, in the end, because both A and B were 1, so the result should be 0, carry 1. So far, so good. So let's consider, and that will be, so it works with both of them being 0, with one of them being 1, and with both of them being 1, right? And so far, the carrying we were considering 0. Now, let's say that they're all 1, yeah? So A and B together, so if A and B and C, the result should be, so we're adding 3 ones, it should be 3, which means that the sum or the result should be 1, the S2 should be 1, and the total carry should also be 1, right? And that will make 3. Okay, so 1 and 1 is 1. No carry here. Then
Wait,
the
I
second.
thought A and B, if they're both 1, their sum is 0.
Yes, I'm sorry. That is correct. If both, yes, absolutely. So A and B, the sum is 0. So A in the second half there will become 0, but the Cout is going to be 1. Okay. Now the C in is 1. The carry in, we plug it directly right into the second half adder. So we have 0 and 1 is 1, right, which is what we wanted in the sum. And the Cout here, C2, is 0, right? But the first one was 1. So when we OR them, we get 1. So we'll get 1 and 1, right? And, because as I said, the carry is the next digit to the left, it's worth 2. We get 1 and 1, which is binary 11, which is decimal 3, which is what we want, right? So let's look at it more formally, right? So if the C1 here is 1, that is the same as A1 and B1. So so that will produce, both are 1s. C1 is going to be 1. And that is the same, or in this condition, the S1 is going to be 0, right? If both A and B are 1. And carry out 2 is going to be 0. So C1 and C2 will not be 1, right? Only one of them will be 1, right? Because if both A and B are 1, then the second carry out is going to be, let's see, the second carry out is going to be 0, right? Otherwise, so basically, no more than one carry out, either C2 or C1 can be 1, right? They can both be 0, but both of them cannot be 1, just logically. So because both of them cannot be 1, we must use the OR gate, right? If there was a possibility of them being both 1, that we possibly could use an AND gate, right? But if we use an AND gate, even if one of them is 0, the whole thing would be 0, right? And it would always be effectively 0. But in order to produce 1s, it has to be an OR gate. So here it is. We connect C1 and C2, the two carryouts, with the OR gate, with the plus, and that produces the resulting Cout. Okay. Now we can put a big green square over it, and put a drop of epoxy, it dries, and now we have a full adder, and we can make more of them and then put them together. And if you put a bunch of them together in a row, then we can, as many as we want, and we can add two binary numbers of any length, of any magnitude. Okay. So I hear a question coming up. Yes.
Yeah, sorry. I think you mentioned Claude Shannon at MIT. Was this the stuff that he did, or is that a different part of the class? Do you happen to know?
That was in the very first lecture, and yes, I think he actually I think he used logic to make the circuit. He used the formulas of functions of Boolean logic to make the circuit simpler, right? So it's sort of like all three of those, fathers of computer architecture. We're using all of their work here. We're putting all of this together. Standing on the shoulders of the giants. Okay, so now we can do a formal proof, right? So in the half adder, we can express this half adder in the formula as two functions, s and cout, right? So s is going to be 1 only if one of a and b is 1, right? So let's pause here, and I want everybody to see that. Right, the sum can only be 1 and 0. So if both of them are 0, it will be 0. If both of them are 1, what will the sum be? We're looking at the half adder. Somebody else, just the simple question. So this is the half adder.
Should be 0, somewhat.
Should be 0, right? So the only possibility for the sum in a half adder to become 1 is that either it's not a and b, so either a is 0 and b is 1, or a is 1 and b is 0, right? So that's the function, representation of a half adder's sum as a function. And now we need the second function for the carry, right? And carry can only be 1, carry out, when both a and b are 1, right? If both of them is 0, c is 0. If one of them is 0, c is 0. Okay, so these are the functional representations, Boolean function representations of the one half adder. Right? The second one is exactly the same. So in the proof, for the full adder now, right? For the full adder, it's a little bit more complicated, right? For this whole green box, big green box, or here it's the same, where it says full adder. The full adder, the sum is going to be 1 only if just one of these three inputs is going to be 1, and the other ones must be 0. So it could be A0, B0, C1, or A0, B is 1, C is 0, or A is 1, B and C are 0, or if all three of them are 1, right? If all three of them are 1, then the total number is 3, and that means that the resulting carry out has to be 1 also. Okay. So as I think I asked you and somebody answered yesterday, for the full adder carry out, the number of ones in the inputs has to be odd, right? It has to be 1 or 3, and if it's 0 or 2, this resulting carry out is going to be 0. So here we have the sum function for full adder. Now we need the carry function, right? Sorry, I was talking about sum before, right? So the odd and the even is about the sum. Okay, I misspoke. So for the carry, in order to be 1, we need to have a situation where any two of A, B, or C are 1, right? And the other one doesn't matter. Now we can plug in these formulas into the second, or we can take the half adder formulas as inputs to the second half adder and produce a longer formula that we can eventually simplify. So for the first half adder, it gets raw inputs A and B. It's the same formula here. Now, and for its output carry out for the first half adder, again, it's exactly as here as AB. I'm just repeating them. But now for the second half adder, in order to get the sum, we need to use its own A and B. But their own A and B, A is S1, and B is the carry-in into the full adder, right? So it's the same formula, but instead of A's and B's, we have the first sum and the first carry, and the first carry in, and that are the two inputs that go into the second half adder. So it's the same formula, but with different letters. Now we can substitute S1, right, in this formula with this representation of S1, right? So S1 is identical to not A and B or A and not B. So we're going to plug that in here and here. So we're going to get sum of factors, right? Where the first factor is not A and B or A and not B multiplied by C in. We kept it as it is, right? Because it's one of the raw inputs. Or not A and B or A and not B also multiplied or and the same C in. So the first homework assignment from today, and this is easy enough. This is just conversion, so I definitely want you to do it by tomorrow. Is to finish this proof, right? We're almost there, right? You just keep going and simplify it as far as you can, right? And show that the total sum here is going to be equal to S2, right? And from the diagram, it looks apparent, self-evident. But if you finish this formula, you'll get the actual formal proof, and that C out, the resulting C out is equal to C out 1 or C out 2. Okay, so that's the first assignment. Any questions about that? Right? Any questions about any of that? Before we go to the next thing, I want to make sure that everybody was on board here. Sorry. You can start asking questions while I'm populating the screen again. No questions. Everybody is good with this. Excellent. In that case, I can go to the next slide. I'll do that directly. All right, everything is straightforward, very logical. Okay. Now, in this slide, we're going to see a different implementation of a full adder. Right? And there can be, maybe infinite number of ways you can implement something using gates, logical gates, but of course it will become ridiculously complicated and expensive for no reason. So the companies that actually make chips, like IBM, they use proprietary compositions of their circuits for whether it's adder, subtractor, etc., right? And they keep them secret. So at some point, IBM released one of the diagrams that they used in the past. They don't use it anymore. So the one that they're using now is secret. But it can be too complicated. In any case, this is the old IBM's processor version of a full adder, right? Where it takes A, B, and C, A, B, and carry in, and comes out with the sum and the carry out. Why did they do it this way? I don't know. They had their reasons, manufacturing. It seems a little bit actually more complicated, possibly, than ours. However, once it's all sealed, right? It's a black box or a green box. Its functionality is exactly equivalent. So the second assignment is to prove that this IBM monstrosity is indeed a full adder, right? That prove the fact that it works, in the end, if you don't look inside, exactly the same as our full adder. So how would you do this? You would come up with a logical expression that will have 5 ands and 3 ors and some knots, right? Primes, right? And then put the right parentheses around them. And to do that, and we'll have 3 inputs. And to do that, you'll have to trace all of these wires. Remember that when we have a dot, that means that the wires there actually intersect, and in fact they act as splitters. For example, this dot splits B into 2, right? And then if there is no dot, then they don't touch each other. They just go above or below. Any questions about this one?
I'm sorry, why is that inferior to the previous?
It may not be. I don't know. Well, this is more detailed, right? Because in our full adder, we assume that we already have half adders, right? But these half adders that we just work with them as red boxes, inside they have a bunch of gates also. So in fact, IBMs may be less complex. But as I said, there are many ways to do it, and this is the way that they chose because of their manufacturing process. So you can try to come up with another one. The fact is that what you would do is you would simplify these two formulas as far as you can get them, right? You would get 2 minimal forms of these, right? And then you would convert those 2 minimal forms into the circuit, and that would be, well, let's say the simplest possible circuit, right? But that circuit may not be the fastest, or it may not be the cheapest to manufacture for some other reasons. Does that answer your question?
Yes, thank you.
Okay, good. So that's the second assignment. Again, I think neither of them are difficult. You just have to follow the steps. And then, of course, to prove them that they're the same, right? Once you come up with the whatever long equation you get from this, converting this just step by step into an equation, then you bring it to its own minimal form, and the minimal forms will have to be the same. And these are the minimal forms, right? These are the minimal forms of the full adder. They cannot be minimized any further, I don't think.
I have a question.
Yeah.
So on an exam, would we have to break down, for example, what half adder 1 could be and what half adder 2 are made up of? Kind of like how it's in IB.
Oh yeah, I understand exactly what you're asking.
Yeah.
So yes, I may ask you to do something like this, right? And that's a good question. How would you do it? Well, I'll ask you, what would be your first step if I ask you to do that? So I tell you, well, as you remember, the way the half adder works is that it takes A and B in and produces sum and carry out. It has 2 inputs, 2 outputs, meaning that if I wanted you to make it, right, you would need to first come up with the functions for it, right? I mean, these are the functions, and you may just remember them. But if you don't, how would you go about it?
Well, I mean, it seems pretty straightforward in terms of just like if you want S to be, if S is going to be 1, it has to be A and B. If like for C out to be 1, or sorry, no, for S to be 1, it would be like A,
Right.
not A, B,
Yeah,
or yeah, not
yeah,
B.
exactly. Yeah, that's exactly right. But right now you're sort of like juggling them in your mind, and it's hard. What is the easy tool that we have to like make it easy to break it up?
A truth table?
A truth table, yes, exactly right. Right, so you would start with a truth table. Once you have the truth table, that allows you to, you know where the ones are. That allows you to make a little tiny K-map. and that will allow you to make a little, the simple formula, right? You would get this. You would get for the half adder, and of course there will be two separate truth tables, one for S, one for C. Now, once you have the minimal formula, you simply, substitute. What you have here, you have a not, an and, an or, an other and another not. Those are your gates, and you just connect them, and you got it, right?
Yep. Thank you.
Okay. Good. Obviously, again, I think time constraint was a big issue on the exam, so I'll try to, not make any question too long, to answer, and then I'll try to figure out the total amount of time that is sufficient to answer everything. Okay, so now it becomes a little bit more interesting, right? As I said, once you have these full adders, you can stack them, right? And now we're going to do that. Let me check the time. Okay, Mr. Okay. In order to make it to my next lecture, I'll have to let you go a little bit early, but we still have time. We still have time, so let's do this. So suppose we have a 2-digit binary number, right? So not just 1, but 2. So for example, we want to add 2 and 3, yeah? So 2 is 10, 3 is 11. We want to add them, okay. Or let's say it has 3 digits, right? So however many digits, right, we're going to have that many additions, right, and that many full adders, right? So we're going to break the A number, however long it is, and the B number, however long it is, into individual bits, right? So the least significant bit for both A and B are going to be A0, B0. The second least significant bit is going to be A1, B1, and then A2, B2, A3, B3, et cetera, until the actual most significant digit. Everybody's clear on this, right? Okay. And now we're obtaining the sums, right, of all the pairs, and again we will get the the least significant sum, then the second least significant sum. We'll get the sums. Right? So using binary full adders, by adding them bit by bit, starting with the least significant digits, right? So here we have a full adder that can add, we don't know how many bits, like a long number, like you see a dot, dot, dot here, but the longer the number is, just like more of the same, right? More of the same, more of the same, more of the same. And when let's say that you want to be able to add 10-digit binary numbers, and you made this device that will have 10 full adders inside, yeah. And then you seal it and you treat it as a green box, and this whole thing, let's say that right, it can add a 10-digit binary number, right? So it will have inputs for all A digits and all B digits, and they will be coupled, right? So that means that if we had a 10-digit binary full adder, it would take how many total inputs? Quickly. Okay, on this picture, it's a 4-digit binary adder. How many inputs does it take? Just count them.
None.
Well, yes and no, right? It will have 8 actual inputs that are variables, right? That could be anything. The 9th input, right? You need to have, so the carry input for each of these full adders will carry internally, right? Will result from the outcome of the previous bit's full adder. But for the very first full adder, the least significant bits, we only have A and B. We don't have a carry out from less significant digit, because there is no less significant digit. We only have you know, A0 and B0, right? For that reason, we're going to hardwire the first carry in to 0, right? So it will always be 0. Does that make sense?
Yep.
So we shouldn't consider it as a, you know, a variable input, right? So in fact, there is only going to be 8 inputs here, or what it's going to be, the number of inputs will be exactly double, you know, the number of digits, right? So we need to have an input for each digits in each of the numbers that we're adding, and then how many outputs? Well, we will have as many outputs and as their pairs of digits, right? So exactly half of inputs, right? So under, you know, if we're doing the long addition, under each pair of digits, we're going to have exactly 1 digit, right? So it will have that many sum outputs. Right? Notice that every of these full adders produces its own carry out, but that carry out gets, you know, passed along to the next full adder, so it doesn't come out. Right? What about the very last carry out? Yep, that one has to come out, and we'll call it overflow signal. Why do we call it overflow signal? I mean, we know what it is, but why is it overflow, right? So we'll just follow this picture, pretend that there is no 3 dots. So we have a 4-digit full adder. That means that it can add 2 4-digit binary numbers, right? And it'll do it correctly. And then it's possible that after the last addition, there is going to be a carry out, right? And here it is, right? So we have, you know, 4 sums and 1 carry out. Why did I call it overflow?
Is it because, like in the case of 4 digits, it would be possible to end up having 5 if there was enough ones, and so we can't do that with 4 adders. So it's an overflow.
That's right. Well, no, we can do it with 4 adders, but we cannot do it with 4 bits reserved for the sum.
Oh, yes.
Right. But that's right. That you had the right thought. It will overflow, and we will lose it unless we make arrangements, you know, to have an extra bit, right? But if we just adding, you know, 4 bits and 4 bits, and at the bottom we have space for 4 sum bits, and it absolutely could and will happen that you will have the last carry out, another one that really you should catch somehow, but if you don't, it'll just overflow, and you know, you lose it and you'll get the wrong answer. Okay, I think that was pretty straightforward. Were there any questions about that slide? No. So now addition, as I said before, is simpler than subtraction, but you know, we have to be able to subtract, so we will have to build the subtractor, right? And to build the full subtractor, you first have to build the half subtractor. So let's look at how half subtractor will behave. So half subtractor, you subtract 1 bit from another. So it will have 2 inputs, A and B, and we're going to try to subtract bit B from bit A. And there will be a result of subtraction, the difference, or whatever you want to call it. But there also, in order to do this, you may need to borrow, right? And for borrow, we call it borrow out, we're going to use the symbol beta from Greek alphabet, right? So it's not carry out, it's borrow out. You need to borrow. And that borrowing is tricky. But we think of it as having 2 inputs and 2 outputs. So like half adder, it has 2 inputs and 2 outputs. Again, if there are questions, just stop me right now. Now, we don't know how it works yet, so we're going to start, as I suggested before, if you have to do something like that on the exam, by building a truth table, right? 2 outputs equals to 2 functions. So we have 4 possibilities of combinations of A's and B's. So if we want to subtract 0 from 0, the difference is going to be 0. And there is no need to borrow anything. So the borrow out is also 0. If we try to subtract 1 from 0, what will we get in the difference and the borrow? Right, I'm subtracting B from A. So if I have, you know, if A is 0, B is 1, and I'm trying to subtract, what will happen?
B will be 0, and the other one will be 1.
So we need to borrow 1. The borrow out is 1. That's right. And if we borrow 1, then the 0 becomes a 10. And when we subtract 1 from 10, we get 1. I think that's what you said, right? So we need, or if you didn't, that's fine, but this is what will happen, right? In order to subtract 1 from 0, we need to borrow 1. Either carry out or borrow out are of higher significance, right? So when we borrow 1 and put it in front of the 0, it becomes 10, or binary decimal 2. And when you subtract 1 from it, you get 1 decimal or binary, right? So that means that your difference is going to be 1, and your borrow out is going to be 1 as well. Questions about this? Okay. What if we want to subtract 0 from 1? And that's easy. The difference is going to be 1, and we don't need to borrow anything. Okay. What if we need to subtract 1 from 1? Right? That's easy. 1 minus 1 is 0, and we don't need to borrow anything. So this is the behavior of the difference function and the borrow out function. Any questions? Now we can, I'm going to skip the K-map step, but now we can simply convert it into the formula, right? So D is only going to be 1, right, in the condition where not A and B or A and not B, right? Is that correct? Did they make? Oh, difference. Yeah, that's right. We have 2 1s here, right? So we have 2 1s, so we're going to have 2 min terms, right? So the first one is going to be not A and B, or the second one is going to be A and not B.
Isn't this the same as the half adder sum?
Is it the same? Maybe, but I don't like my head hurt. I don't want to. Let's just concentrate here. I mean, yeah, it's similar to a lot of other things. So, for example, this formula, what else is it? Or this particular truth table result, 0, 1, 1, 0. Is it an AND? Is it an OR? Is it a NOR? Is it an AND? Who can tell me?
Isn't it XOR?
It's XOR, yeah. So in this case, you can represent the difference function by a single XOR circuit. Now, in the end, that may not be the simplest way to do it, but it will certainly work. Okay? So if both of them are 0, it's 0. If both of them are 1, it's 1. But if only either one of them are 1, so either or, but not both. Yeah? So that's what you get. And of course, for the beta, for the borrow out, yeah, it's a single one, so just a single min term, and it will only happen when you're subtracting 1 from 0, so not A and B. Okay? Okay, now let's make, let's find out what should full subtractor do. Now, like the full adder, it will have 3 inputs now, right? Yes, you're subtracting B from A, but you may also have something that was borrowed, right? That would be the third input, borrow in, right? You have the A, the B, the borrow in, meaning that your less significant neighbor borrowed it from you, and then the outcomes are the difference and its own borrow out. Yeah? So now we're going to come up with a truth table for both of them. Right, this is the truth table with 8 rows. So effectively, what we're doing is we're not just subtracting B from A, we're subtracting B and borrow in. Right, so both of those things have to be subtracted from A. So 0 minus 2 zeros is going to be 0, no borrowing. 0 minus a single 1 is going to be 1 borrowing, and result 1. This will be the same, right, just different combination. We're borrowing 1. Now we're borrowing 2, right? To borrow 2, we need to borrow, to subtract 2 from 0, we need to borrow 1, right? So we would borrow 1, then the 0 becomes 10, right? 10 minus 1 is 0. Okay, if it's unclear, stop me. Then we subtract zeros from 1, no problem. 1, nothing to borrow. Then we subtract 1 from 1, no problem. We get 0, nothing to borrow. Now we again, same thing, subtract 1 from 1, 0, nothing to borrow. This is the trickiest one. We need to subtract, well, it's not tricky, actually. I guess this was the trickiest one. We want to subtract 2 from 1, right? We need to borrow 1, make it 11, 3, and subtract 2 from that. That will result in 1, and we have to borrow 1. Any questions about this? Okay. Now let's convert this to mean terms for the difference function and then for the borrow function. And I'm going to assign you to that, right? Again, if we just it's sort of like almost as simple as we did here. You'll get the D and the borrow out. They'll be a little bit longer in their minimal forms, but
everyone's connection is glitching right now.
Okay. You still see the picture?
Yeah, but we hear like every other word you say.
I'm saying, okay, let me repeat. Is that still the case?
Yeah, it is.
Yeah, okay,
Yes.
it's getting better slowly.
Okay, I don't forget that. So let me just slowly try to repeat what we said, is that together we just found out the minimal forms for E, for the difference and the data, and the borrow, the difference and the borrow out for the half subtractor. And I want you to, at home, this is the third assignment for today, to find out these same minimal forms for difference and borrow out for the full subtractor. You would do it the same way, right? You will look at this truth table, and then each one for them will become a mean term, right? So for example, for the D, the mean terms are going to be not A, not B, and beta, not A, B, not beta, not A, not B, not beta, and A, B, beta, right? So those are the three mean terms for difference, and then we have four mean terms. I'm sorry, there are four mean terms for difference and four mean terms for beta and borrow. Okay, and then you try to simplify them. Okay. And again, the last one, I don't expect you to be able to do everything until tomorrow, is to actually construct a full subtractor using only half subtractors and one other gate, right? So you should try to use two half subtractors to make a full subtractor and one other gate. So the same as we did for the other today. I'm not going to. Yeah.
Explain the table again, like the difference in borrow.
Table.
Yeah.
Okay. So for the full subtractor, yeah, I'm not going to start comparator today. I'm going to do that tomorrow. But for the full subtractor, you're subtracting from A. What are you subtracting from A? B and the borrow in. Does that make sense?
Yeah.
So in the half subtractor, you're subtracting B from A. And if you need, you borrow out. You borrow from the more significant digit in front of you. But for the full subtractor, yes, you subtract B from A, but also you need to allow your least significant neighbor to borrow from you, your less significant neighbor to borrow from you. And that makes it from two input device to a three input device, right? But of course, there are only two outputs, so there are two functions. And you just go step by step, combination by combination. You're subtracting, let's say, the sum of B and borrow in from A. So subtract zeros from 0 is 0, and you didn't have to borrow anything from borrow out. Subtract 1 from 0. You need to borrow 1, and you get 10 minus 1 is 1. Okay. And the next one is the same. You're subtracting 1 from 0. So again, you get borrow 1, result 1. Now a trickier one. You need to subtract 2 from 0. Right? It's not 11, it is 2. From 0, it is individual bits. You subtract 1 and then subtract another 1. So to do that, you need to borrow 1, right? We'll make it 10. Minus 1 minus 1 is 0. Right? 2 minus 1 minus 1 is 0. Then this one is easy. Your a is 1, and you subtract 2 zeros from it. You didn't have to borrow anything. The result is 1. And here, a1 is 0, borrow n is 1. So you subtract 1 from 1. You didn't need to borrow anything. The result is 0. Then, similarly, a is 1, b is 1. There was no borrow, so you subtract 1 from 1. You didn't need to borrow anything. The result is 0. And here we have a situation where a is 1, b is 1, so we just subtract 1 from 1 is 0. So far, so good. But then we also need to subtract the borrow in. Right? At this point, in order to do that, we'll need to borrow 1. So here's the borrow.
So the last one would be like a 1 minus 2. Or we need to borrow 1.
Yeah, in order to do 1 minus 2, right, in binary it's going to be, 1 minus 2. So first you subtract the first one, and the 1 becomes 0. Okay? Then you go to subtract the second one, now you need to borrow. So here you borrowed, and now you borrowed, and your 0 became 10, and now you can subtract 1 from 10, and you get the result 1.
Okay, that makes sense. Thank you. Also,
Okay, very good.
I think your screen might be frozen.
Oh. Well, I guess let's pause. Let's stop here, right? I think that you were able to get everything that we've covered so far, the adders and the subtractors, right? You have the homework, the new homework assigned. I'm going to open 2 links for homework. There will be 1 link for this new homework and 1 link for previous homeworks that are outstanding in your case, and you can just submit those 2 things. I don't expect everybody to be able to finish all 4 new ones. Do as much as you can. But you can catch up on reading over the weekend, a long weekend. And tomorrow I'm going to start with the comparator. It's another device. Okay, so if there are no questions, I'm going to sign out and head to my next lecture. Right, so I'm letting go a little bit early. Any questions about anything? Okay, this is what I would like you to do right now. I would like you to do 2 things right now. I would like you to take a screenshot. I would like everybody to take a screenshot of the slide where you have assignment 18.3, 18.4. Make it bigger.
Professor, I have been having internet issues like for the past 5 minutes, I think, and I literally can't see your screen. I came in and out. I turned off my internet, came back in. It just doesn't show up. So.
Well, hold on. I'm going to.
Yeah, I'm in the same situation.
I'm going to unshare and share again. I'm going to also turn off my video. Okay, so share application screen. Can you see it now?
Yeah.
Okay, everybody take a screenshot of the slide. The slide has the 2 subtractor truth tables and formulas, and then assignment
I just see
18.2.
you streaming Blackboard. I don't see the slide. Okay, there we go.
Okay, once you take the slide, please take a screenshot. Okay, who hasn't done it yet? Right now, I want to move to another slide, so you take a screenshot of that. Everybody took a screenshot. This one. Take a screenshot of this one. It has 18.2. Everybody took a screenshot of this one. And this one has 18.1. Let's make sure that you see it all. Hold on, let me, no. I'm going to slide it. Okay, I take a screenshot of this now. Okay, everybody took screenshot of 8.1.
We're still only seeing 18.3 and 4.
Okay. I'm going to unshare it again and share it now. Okay, do you see it now?
Yeah.
Okay, everybody please take a shot. A screenshot. This slide has 18.1. Okay, everybody take a screenshot of the slide. And now I'm going to go to the last slide that we need to screenshot that has 18.2. Everybody take a screenshot of this. And now can you see this 18.2?
I don't see 18.2.
How about now?
Nope. Still 18.
Okay. Okay, I'll do it again. Okay, now
I
it
also
should
posted
appear.
the screenshot in the Discord for everyone.
Okay, thank you. I appreciate that. But everybody still take a screenshot, and this is the last one. Okay, all right. So I will see you tomorrow, and we're going to do the comparator, and then we'll start the new topic as well. Okay.
Professor, I just want to remind you to stop recording.
Yes, let's do that. Let's stop recording.
Professor, could you also open up the homework